Riley, who's our director of science. I stole a number of these slides from her, so she was very generous in helping me put this together. So just a little bit about what ALCF is. ALCF is a national user facility funded by the Department of Energy, and so there are kind of three things that ALCF does. The first and the thing we're most known for is fielding leadership computing. So we put all of these big computers on our floor and make them available to people. But really what people come to us for is the expert support. And so we have computational scientists and visualization experts and performance engineers and data scientists that help people use these big computers and make use of them in lots of different scientific domains. And then we're also always looking at the next generation of computers and what should be on the floor next. And so we have small test systems, and then we field very experimental, serial number 1 and 2 machines. And along with that, we're always developing the software stack that supports that. So both the kind of infrastructure support and scheduling and debugging and all of the tools that go with this. And this is kind of a virtuous circle. So when the next machine comes in, we put it on the floor, and then we use our experts to help design the one after that. So that's the fast commercial about ALCF. These are our systems that are currently in place. So Mira is our workhorse that's been around since about 2013. That's an IBM Blue Gene Q. And then more recently, we've got Theta, which is an Intel system built for us by Cray that is about the same, around 12 petaflops, about 8 petaflops peak. But what you probably want to hear about is the whole future system. So there's a system coming in 2021 named Aurora. It is part of the Exascale Computing Initiative. I think Doug Cothey went through this a little bit, but Doug talked about that kind of gray box up at the top, the Exascale Computing Project. So that's the part of ECP that's really developing the R&D. So it's not the purchasing of the machines or the siting of them or the support. It's really the development of the software and infrastructure that's needed for Exascale. Where ALCF sits is mostly in this kind of brown box here, the facilities. So that's where we deploy these systems, but we're also working with the vendors through non-recoverable engineering investments to pay money into the vendors to build exactly what we want. And so all of these kind of taken together, so the R&D effort, the build effort, and the deployment effort are collectively called the Exascale Computing Initiative within the Department of Energy. And this slide, how many times have you seen this slide this week? I think this is at least the 3rd or 4th time I've seen it up here. This was all stolen from Barb Helland, who is a program manager in the Office of Science, who gave it at an ASCAC committee meeting about this time last year, I think, around sometime late in 2017. So this is kind of almost a summary of what I'm going to talk about, but you can see the motivation for ECP and the motivation for putting Aurora in place is the 3 pillars here. You can see some of the timeline, and I'll talk about that, and I'll talk also about the process. Okay, so why do we need these machines, and what are the requirements? So simulation is the thing that's the bread and butter for all of our facilities and most of the people in this room. And we're looking at putting a system in place that's about 50 times faster than the kind of current systems at ALCF, even 10 times faster than the new Summit system at OLCF. So the idea is to put a machine in that's really a leap in power. And the typical kind of users are CFD, flows, cosmology, weather. Some of the new emerging things are around quantum computing, so not doing quantum computing, but simulating quantum computing. And then a lot of stuff around brain and genetic modeling that we're starting to do. So I tried to put as much of the kind of hard requirements as we're putting in place on the Aurora system as I could there. These are kind of, pretty general numbers here, but the things to point out is that much increased computational intensity and floating point intensity, especially for simulation, increased memory bandwidth. When you get down lower here, we need very low bandwidth communication. So that drives our networking decisions. So instead of just buying commodity networks, we basically have to build our own network to get injection bandwidth of hundreds of gigabits, latency across the entire machine of microseconds. That you can't just do that with off-the-shelf parts now. But then when we start looking at data analytics, the requirements change some. So we're doing a lot of this now. We're taking things, and these are some examples of things that we're doing already. So data from the Advanced Photon Source, things from the LSST or the Atmospheric Radiation Monitoring Project that's at Argonne, high energy physics detectors. These are all generating huge amounts of data. And that drives a little different architecture. So if you look, you need much more streaming I/O bandwidth. So you're getting into the tens of terabytes a second of data bandwidth. You need much more memory, and you need it to be coherent. So that drives something that we haven't seen in simulation machines. You need things that are much more interactive. Santanu mentioned he's been promised 10% of the machine. I hadn't heard that, but it's good to know. And that drives a whole different architecture. When you start having process flows that are in and out of the machine dynamically, it really drives a little bit different architecture. And then you were looking at things about embedded capabilities around machine learning. These machines have always had embedded capabilities around multiple floating point units, things to accelerate computation, but machine learning is a little bit different, so we want to accelerate that. And so in machine learning, I really don't even have quite the level of specificity that I do for the other two areas. This is really an emerging area that we're learning how to do on big supercomputers. If you look at Summit, it's a really good machine learning environment. But coincidentally, it wasn't necessarily designed to be a machine learning environment. It turned out to be very good because they were designing a balanced system. But in this case, we're really trying to look at machine learning as a first-class citizen as we design this system and what the impact will be. So there are some things that are driving our thinking. All right, so this is one I stole from Catherine Riley, and I really like the way that it relates all these, because one of the things that people always talk about is the pillars. And so, the pillars are data analysis and simulation and machine learning. They're not really pillars, though. They're interrelated. So we use machine learning to drive our simulations. We use visualization to help inform our machine learning. We use data analysis to build up the capabilities around learning. So these, and I argued with her about where the arrows go. So you could almost pretty much interconnect all of these boxes with others. But the thing to remember in this is that we expect the workload on Aurora to be a combination. So even within a single project, that there'll be data analysis, there'll be visualization, there'll be learning, and it'll all be tied together. All right, so I'll switch over to how ALCF gets one of these systems and where we are along the path. And so it's a pretty well-known path that both the Argonne Leadership Computing Facility at Oak Ridge and NERSC at Lawrence Berkeley National Lab follow. We talk to vendors, we issue an RFP. This is the standard federal RFP where people can respond to with very detailed proposals. We form an evaluation committee. One thing that we've been doing more recently that's a little bit new for DOE is doing in coordination with other labs. So like Coral is the collaboration of Oak Ridge, Argonne, and Livermore, so we all go together to issue an RFP. We start the evaluations pretty as soon as we get them and start choosing vendors. But right about the time that we make a choice of vendors is we start an early science program, and I'll talk about that a little bit in a minute. We issue what's called non-recurable engineering contracts, so we fund the vendors to do the things that are required to produce the system that we want. We issue a build contract, and then we take delivery. That's a fast process. So you've probably seen this week as well. The procurement for Coral, which is procuring A21, is a little bit weird in that it also was the procurement vehicle for Summit and Sierra, which were already delivered. But we had Aurora originally scheduled for about this time, and we kind of shifted the resources and the name and everything for it. So that's why you hear it called A21 in Aurora. And we like to put 21 in there because we really want to put a stake in the ground. We want this system delivered by 2021. And putting it in the name kind of encourages everybody to focus, because otherwise things kind of slip along there. So here are some design points that we're looking at. I also put a little chart there. I was just discussing with someone what the next thing after Exascale is. It turns out to be Zetascale. So we'll be back in a few years to give our Zetascale talk. And then Bronto, it gets weird after Zetascale. But one of the things to look at here is that there are two different design approaches to building an exascale system. So one is to integrate the host processor with accelerators. The other is to kind of integrate separate accelerators into it. And so these are two different approaches. And if you look at the way the Department of Energy funds these supercomputers, they want Oak Ridge and Argonne to have different architectures. And so clearly when we get into the exascale space, one of us is going to end up with an architecture where there's an offload style to acceleration, and the other will end up where the acceleration is more integrated into the chips and into the core processors. A lot of the other stuff here is probably common among both systems. We're expecting a mixture of high bandwidth memory, maybe exclusively, maybe in conjunction with other types of memory. We need a lot of it. One of the big cost of a supercomputer is just memory. So we would basically get all the memory we can afford. The power requirements, let's see around here. We're trying to stay kind of in the 30 or 40 megawatt space on these. Storage will probably be almost all solid state, maybe a little spinning disk to the side, but the advantages of solid state are important in this. This is another kind of representation of some of the stuff I'm talking about. We're expecting the number of nodes to not increase tremendously. And so if you look at like Mira had about 50,000 nodes, the same power to get Theta, also around 10 petaflops, is only in the order of about 4,500 nodes. And so we expect in exascale that we're not going to really go a whole lot more nodes, but we'll get a lot more core density. And so that's, you can see the compute we're expecting to be kind of 20 times. So there's a lot more parallelism. We're expecting to get more memory bandwidth. So you can see over to the right that, and there's intentionally not really kind of a scale to the left. This is just trying to give you a rough idea of what we're looking at in the increase. So memory will go up a lot, power will go up some. We're not expecting memory per node to go up a whole lot, and so we're still going to be in a memory limited environment. So I'm going to leave this behind. We'll put it in the whatever repository Earl collects all of these into. So you can read this later. This is approved by Intel, what I can say. You may be able to Google and find more information than I'm allowed to say. So feel free to Google away, but I can't really confirm or deny anything that's not up here. But the thing to point out in this is that we are expecting Aurora to have a lot of concurrent parallelism that you can take advantage of both on a very fine-grained and a more coarse-grained. And so if you're preparing your code for systems like Aurora, working on concurrency and parallelization is going to be really key. And so we're looking at automated ways to do that. There'll be automation both in the hardware to optimize and in the compilers. And so it's very key to take advantage of as much concurrency as possible. Memory bandwidth and performance, we're expecting to go up kind of together, but memory capacity will not grow as fast. And so you'll still be in a pretty memory limited environment. We're trying to keep bandwidth between nodes up as much as we can, but that's a challenge as well. Networks are not increasing quite as fast as we'd like. All right, so that's kind of the hardware. So what are we going to do with this? And we've already started worrying about that. So ALCF and OLCF and NERSC all have versions of early science program. This is just kind of an overview of what it does. The real component to the early science program is these dedicated science teams that have committed to using hardware. When they start out, the hardware doesn't even exist. They're working toward an ideal, and then the hardware kind of becomes available in test forms and in simulators. And so people work through all these with their codes. We assign dedicated computational scientists to these projects so that they have all the help they need, and so we get input right back from them. So we've already started the Aurora Early Science Program, even though we don't have any real hardware to talk of right now, but we have some knowledge of how the hardware will look, and so we're working with these programs. We chose 5 simulation projects quite a while ago. More recently, we've announced 5 data and 5 learning projects as well. Like I said, each of these get a dedicated postdoc that is assigned to them. They get extra support from ALCF. They get a lot of input from vendor. They get incorporated into our non-disclosure agreements with vendors. So they get a lot of help to make them successful. You can see on the timeline here, you can see the data projects, the learning projects. And the thing to point out over on the right, so we have the early science program, but then when the hardware actually shows up in, let's see, can you see this? Okay, well, anyway, when the hardware shows up in 21, we start early science, which includes the early science people, but it also includes a kind of a set of friendly users. And so we'll start opening up that. So, but we're already starting training for the early science program teams now. So here's a list of the projects. I will not go through all these, but just to give you an idea of all the different domains that you can see in the traditional simulation. So it's the things, somewhat that you'd expect, things around CFD and around weather and climate and around people working on stuff in astrophysics, fusion. A lot of these people have been very experienced in the community, and so we're relying on them to help us guide development of Aurora. And these are the new projects that were just announced probably about a month ago in data science and learning. And so some of them are overlaps. So if you look at things around astrophysics, they're here as well. But we have some new areas as well. And so we have things, let's see, the in situ fluid simulation there, some of the things around the Atlas detector. So we picked up high energy physics. And these are intended to merge both simulation and data learning and data science into this. And so the people doing it are experts in kind of both fields. And this, if you look at the right-hand column there, this is really an eye chart, but these are the different areas that we've identified, and we have ECP applications on the right, and then you can see the data science and simulations there. So we're trying to cover kind of as much applications. And what's not in here, we also look at the techniques that they're using across the different things. So we're trying to really capture a broad variety of people. So what we're doing as we go along here is widening the community. So we have small groups of people in ALCF that are in red that have the capability to access very restricted information from our vendors, from Intel and Cray, very early on. And we share that with a few people at national labs. So that's pretty much where we are at this point. We've shared this information. We've got small groups of people using it. We're kind of now just starting into kind of the yellowish, brownish colors here. We've got the RFP review teams have finished their work, and we're in the process of negotiating the NRE and issuing the NRE and the build contracts. So we're starting to widen it up a little bit, and people are getting more access to very specific, very detailed information that's only available from the vendors. And like I said, there's getting to be a little bit of information in the press about what is coming. The next step is we widen to other people at ALCF, and we widen to other people at DOE Labs so they can start planning all their applications, and so people will start getting more and more access. And then when finally Intel and Cray announce various things and kind of take their wraps off, we end up in the green. And so we start dealing with users who are outside our traditional communities. We start sharing things with them. We start doing training classes on the new hardware. We start issuing papers. We've got papers already that are kind of written but are embargoed in different ways, or information is not available to the public yet. And then there's something called the Intel Extreme Performance User Group, which Intel helped form but is an independent organization. And so we'll be using that to share all of the information that we know and let people share experiences on Aurora. So it'll be a place where people can come and kind of share information and get information as well. So we're going that direction. All right, so in conclusion here, Exascale is marching forward. The thing that I want to communicate most, and the thing that Catherine Riley, when we were going through this presentation, stressed, is that we have a definite plan. We are on the way there. We're working with vendors. We wish we could say more exactly about what the architecture is and exactly how we'll deliver it and how it will work, but we're sharing as much as we can. So keep listening. We'll release things as we go along. as we go down that colored funnel. A big thing to remember is that data science and learning are now first-class applications in our HPC environment, which is kind of a first for us. We've always built these systems as just giant simulation machines. So it's both a challenge and an opportunity. So it gives us some capability to do things we've never done before, like doing streaming as a process is going in. So you won't necessarily have to sit in a queue and wait for your simulation to finish. We have all of these large application readiness programs that are going on. And more than in the entire experience that I've had with high-performance computing in my career, the software is being ramped up at the same time that the hardware is. So a lot of times, we put a little bit of effort into the software environment, but we really put all of our real serious effort into hardware. And so we a lot of times get a machine, and the machine's there, and then we figure out how to use it. We were really trying, both through the Exascale computing project and through the early science program, to build the software and the infrastructure around these systems so that when the hardware hits the floor, there will be software that can really run on it. And our goal is not just an exaflop on a LinPack. It's really useful science running at an exaflop. So that's a lot more serious goal than just trying to meet some benchmark. So the last one and the thing maybe to take away is there's going to be a lot of big changes over the next few years. The days when you could buy a supercomputer that looked just like the previous supercomputer, but ran at twice the speed with half the power and a third of the cost is over. To meet these challenges of Exascale, we have to look at novel architectures. We have to look at novel programming environments. We have to look at new ways of communicating between nodes and new ways of building resiliency in. So things are going to change. And that's kind of the fun part. I mean, we're on a new adventure that hasn't happened in the history of supercomputing in the last quite a while. Probably the biggest change similar was going from vector machines to multiprocessor machines. And so we're making about that sort of leap again. So I'll stop there, and I think we have a few minutes for questions. Thanks.
Hey, are there any questions for Dave? Merle?
You mentioned the change in the software stack, which is wonderful, but it could be scary to all these applications that are out there using kind of the old stuff. What's that challenge going to be, and what might the tech transfer methodologies look like to actually help the application community adopt new stacks like this?
Yeah, no, it's a good question. So the Exascale computing project kind of has three different focus areas. So one is around hardware and integration. So that's figuring out what the hardware looks like and how it gets deployed at the different facilities. And there's an application area. So those applications are getting a significant amount of funding to rewrite, refactor, change their systems to work in these new environments. But the third focus area is called software technology. And that's a whole set of, 60 or 70 so different software products that are intended to be picked up by application developers. So they're libraries, they're optimization engines, they're schedulers, there's all kinds of things in the software technology area that are intended to help everybody who has older applications to kind of move along. And so hopefully people's applications can take advantage of different techniques. Either pick up libraries that make their solvers work at exascale levels, or schedulers that help run lots of multiple instances of software. But it's not going to be free. I mean, people, in some instances can just recompile on a new x86 box and run faster. We're not in that world anymore. They're going to have to do something. Though we're hoping compilers will help us some in that case.
Great. So one question I had is related to facilities. I know you can't speak to the detailed system, but thanks for sharing that.
Sure.
Given the 30 to 50 megawatts, are you having to do a lot of revamping for power? Are you going to build a new building? Can you speak at all to the facility side of A21?
Yeah, so I mean, it's not a secret. If you've been to Argonne, there are construction cranes outside our data center. And that most of that work is around power. So we are having to spend quite an amount of money to upgrade power capabilities at our data center. And I think other facilities are working to do the same thing. So every time we talk to Intel, they're like, if we only had a little more power. So I don't even know exactly what our current power envelope is right now, but we are definitely putting a lot of extra power into our data center. And then extra power means extra cooling, right? So you end up in that as well. And so we're improving our cooling capabilities as well.
Any other questions? Okay.
Okay,
Thanks, David.
Yeah, thanks.